here's an infinite sum for 0 to infinity of n factorial quantity squared times 2 to the power of n plus 1 and over 2n plus 1 factorial. So my overall plan is to first, a common approach of dealing with such problems is that we can try and see if we can turn this general term into a definite integral form. Then we can see if we can switch the order between infinite sum and integration. So the fact that we have factorial reminds me of the well-known Wallis integral. Wallis. It says from 0 to half pi, sine, cosine, whatever. So perhaps sine to the power of c. If I have 2n plus 1, it's a single factorial, but if I want to use double factorial, I should write to the power of 2n plus 1 x dx. And the Wallis formula tells us that it is written as 2n plus 1 double factorial, and we have 2n double factorial. Since it's an odd power, therefore we don't have to multiply by half pi. If it's an even power, then multiply by half pi. So again, so 2n plus 1 double factorial means, since odd number means, for example, 9 times 7 times 5 times 3. So it's the product of all the odd numbers from 1 up to this number. It's odd number. So to relate this to that, right, I can perhaps take this and say 2n plus 1 single factorial. Right, that must be, first of all, 2n plus 1 double factorial. Right, then I can write down times 2n, right? Then times 2n minus 2, all the way down to just 2. Right? So this is the product of all the odd numbers from 1 up to this number. And this is, of course, taking out all the even numbers, right? Starting from 2, 4, 6, all the way up to 2n minus 2, 2n. Right, so this is actually, perhaps, I can just write 2n plus 1 double factorial times, I'm going to take out 2. How many 2's? 1, 2, 3, 4, n many 2's. Okay. So 2 to the power of n, and also it's n times n minus 1 times next n minus 2. So I have n factorial. Right. So this is what I have. So I can just replace 2n plus 1 factorial with this down here. Okay. So let me just say, so the inside 2n plus 1 factorial and n factorial to the power of 2 times 2 to the power of n plus 1 can be now written as 2n plus 1 double factorial times 2 to the power of n times n factorial. Now I have n factorial to the power of 2 times 2 to the power of n plus 1. So n factorial, right, cancel out with this one. So I only have one of them, right? 2 to the power of n, 2 to the power of n. I just have 2. I just have 2 up here. So in other words, I have 2n plus 1 double factorial and n factorial times 2. Right? But I'm still trying to relate this to this. Right? So maybe I'll just take the top and rewrite it. So the top 2n double factorial, 2n double factorial. That is equal to, again, that is equal to 2n, like I said, the product of all the even numbers times 2n minus 2. Right, so 2n minus 4, all the way down to 4 times 2. And that is equal to, I'll just again take out the 2's, right? 2 in here, 2 extracted in here. Again, how many 2's? I think it's n many 2's. 2 to the power n times, again, I'm left with just n times n minus 1, and all the way down to 2 times 1. That's n factorial. Okay. So to relate this Wallace formula to this, this is my general term. Maybe I should, first I can just multiply by 2n factorial to the top and divide by the same thing, right? Just to, so my general term, I'm gonna copy it down, 2n plus 1 double factorial, n factorial times 2. That is equal to, this time, like I said, 2n plus 1 double factorial. I'm going to multiply by 2n double factorial, divide by the same thing. Right, but 2n, so times n factorial times 2. But 2n double factorial, like I said, can be written as this, right? 2 to the power of n times n factorial. Right? So now I can just n factorial, gone. And 2 to the power of n, maybe I just, 2 is gone. And 2 to the power of n minus 1. Right, so let me just, that is 1 over 2 to the power of n minus 1 times the Wallace, right, Wallace formula, the Wallace integral, sorry. So integral 0 to half pi sine to the power of 2n plus 1 x dx. Now I've just established this general term. Turns out to be this definite integral. Now, my job now is to calculate for, so I'm looking at the infinite sum from 0 all the way up to infinity of just, perhaps I'll just take this inside the integral. So from 0 to half pi of 1 over 2 to the power of n minus 1 times sine to the power of 2n plus 1 x dx. Right? So I can just switch the order between infinite sum and integral. Right? So that is equal to the integral from 0 to half pi of the infinite sum from 0 to infinity of 1 over 2 to the power of n minus 1 times sine to the power of 2n plus 1 x, then dx. It's perfectly legal. I'll make a video in the future explain why it is, because of uniform convergence. Right? So because first of all, I can just, so what's going on here is that this infinite sum, so really we're adding, so what are we adding up? Right? Just write everything down and see what's going on here. So n equals 0, I have 2 times sine x, right? So n equals 1, I have 1 times sine cube x, right? Then n equals 2, I have half sine to the power of 5 x, right? Looks to me, looks like so 1 over 4 times sine to the power of 7x all the way. Right? So it seems like a geometric sequence, geometric series, right? So what's the common ratio? So I'm looking at what times sine cube x gives me half of sine to the power of 5. Maybe I multiply by half of sine square x. Maybe that's the common ratio, right? Because if I multiply by half of sine square x to this term, that'll give me 1 over 4 times. Yes, exactly. Right? So that is, so this infinite sum is equal to so I have 1 minus the common ratio, half of sine square x. Right? So the common ratio absolute value is in between 0 and 1, 0 and a half. Of course, between 0 and 1, so it is convergent and uniformly convergent as well. That's what makes it legal. So first term, 2 times sine x. Yes. So first now I've worked out infinite sum. Then I say infinite sum, then do the integration, right? First integration, then infinite sum. Now infinite sum, done. Now integration. Now I'm doing integral from 0 to half pi of this. Right? Twice sine x, 1 minus half of sine square x dx. Now, perhaps I'll treat, because sine x dx is, I'm treating cosine x as a whole entity, right? So that is equal to t. So therefore, dt is negative sine x dx. Okay. Then I can multiply by negative 2 on both sides. That will give me the top. Right? So that is equal to x is equal to half pi, t is equal to 0. 1 to 0. And negative 2 dt. Negative 2 dt. And 1 minus half of sine squared, 1 minus cosine square. So 1 minus t squared. That is actually equal to take out negative 2, right? Get rid of the negative sign, switch the boundaries. 0 to 1 dt. That is multiple minus half, right? Negative half times negative t squared. Positive half t squared. Minus plus half, right? Then get rid of the half. Right, that'll give me, so multiply 2 on both top and bottom. That'll give me 4. Right? So just plus 1, and this is just 1. Right? So that's arctangent. So 4 arctangent of t from 0 to 1. 4 times pi over 4. Pi.